Good morning, everyone. We are Group 1. Today, we're excited to present our project, Alpha Trade, an intelligent trading framework that bridges human intuition and machine reasoning. Our presentation will follow four main parts. First, the problem statement. In retail trading, even a few milliseconds can determine profit or loss. Retail investors face massive amounts of data every second. Filtering this flood of information and transforming it into clear, actionable trading strategies is extremely difficult. Most existing tools only cover one stage of the trading process, data, signals, or execution, but rarely connect them into a complete feedback loop. AlphaTrade aims to empower retail traders with institutional-level clarity, speed, and discipline. Our goal is to connect the full pipeline, data, insight, strategy, execution, into one intelligent, self-improving ecosystem. Next, let's move on to the system architecture. AlphaTrade adopts a multi-agent closed-loop architecture, including data collection, hypothesis generator, rule generator, composer, simulator, and evaluator. Together, these modules form a continuous reinforcement-style cycle, from data ingestion to strategy execution, building a complete adaptive workflow. We'll explain each module in detail in the following slides. I will illustrate the reinforcement learning-inspired feedback loop of our system. Unlike traditional parameter training, our framework is model-centric and continuously improves through feedback. First, the system observes the current market state and previous performance. Then, the hypothesis, rule generator, and composer agents collaboratively propose or adjust strategies. Next, the simulator tests these strategies and returns performance metrics. The evaluator analyzes the results and past actions to generate structured feedback. Finally, the system updates its state and starts the next iteration. Through this loop, AlphaTrade adapts and evolves its strategies over time. Now let's move on to the system workflow and see how all the modules interact to form an end-to-end trading pipeline. Here's how the workflow operates in practice. Once the financial data and Chronos predictions are processed, they are standardized and merged to form the final dataset for all downstream modules. The hypothesis model then generates a diverse set of potential trading ideas. These are interpretable hypotheses expressed in our domain-specific language. Next, the rule generator transforms those abstract hypotheses into executable trading strategies, defining precise entry and exit signals. The composer then integrates these atomic rules into multi-factor alpha signals, using logical and mathematical operators. After that, the simulator runs backtests under realistic market conditions to evaluate the performance and stability of each composed alpha. Finally, all outputs, along with human feedback, are passed to the evaluation module, which acts as the system's diagnostic agent. It interprets results, identifies weaknesses, and provides structured, actionable feedback to refine future strategies. At the execution level, we start with data integration. We combine multiple sources, including historical OHLCV data, that's open, high, low, close, and volume, as well as fundamental financial data. All raw datasets are standardized, cleaned, and merged into a unified data structure, which serves as the foundation of our system. Next, we incorporate Chronos, a stock forecasting model. Chronos predicts future price trajectories, and through repeated sampling, it estimates uncertainty levels. These predictive insights help guide hypothesis generation and risk control within the system. The hypothesis agent is responsible for generating trading hypotheses. We designed a domain-specific language, DSL, tailored for trading logic. As shown in Table 1, this DSL translates abstract trading hypotheses into standardized, executable rule expressions. It produces a diverse library of hypotheses, each capturing a distinct market behavior or trading intuition. The rule generator takes both market features and structured hypotheses as inputs. It transforms these into complete trading strategies. As shown in Table 2, the system outputs a standardized JSON rule set. It defines entry and exit conditions, stop-loss and take-profit rules, and position sizing. We also embed risk constraints, such as maximum loss per position, to ensure each strategy remains both practical and controlled. This step bridges the gap between abstract ideas and executable strategies. After the rules are generated, The Composer module combines these atomic alphas into multi-factor signals. It takes both data inputs and rule outputs, applying mathematical and logical operators to transform simple rule-based alphas into more sophisticated composite signals. This LLM-guided reasoning enables the Composer to move beyond brute force combinations. Instead, it builds strategically meaningful and explainable compositions that enhance trading robustness. After that, the Simulator module conducts historical backtesting using the Backtrader library. It evaluates each composed alpha under realistic market conditions, including transaction costs, slippage, and risk constraints, to produce standardized performance metrics such as Sharpe ratio and total returns. As shown in the figure, the strategies generated by the upstream module are simulated in the simulator using historical data to conduct realistic trading simulations. This process validates whether each generated alpha behaves reasonably in the past, ensuring strategy stability for future use. The evaluator acts as the system's diagnostic expert. It uses a dedicated LLM to interpret backtest results, trace performance causes, and generate actionable recommendations for improvement. By integrating outputs from all 4 modules and combining them with real user input, the evaluator provides constructive feedback that drives continuous system enhancement. The evaluation process consists of 3 key stages. First, metric diagnosis, identifying underperforming areas such as a low Sharpe ratio or a high maximum drawdown. Next, causal attribution, tracing these issues back to their root causes in prior stages. For example, poor hypothesis selection can lead to inconsistent trends, while overly complex operators may introduce noise. Finally, constructive feedback generation, producing actionable recommendations like adjusting stop-loss ratios or simplifying trading rules. The results are then sent back to the upstream modules. This closed-loop design enables AlphaTrade to continuously learn, adapt, and refine its strategies over time. The human feedback module allows users to provide natural language comments on strategies evaluated by the system. As a student project, AlphaTrade relies heavily on open source and free tools. For example, we use LangChain to build the agent framework, and Yahoo Finance APIs to collect real-time and historical market data. Next, I'll show a short demo video that illustrates the full workflow of AlphaTrade. We also conducted a detailed performance evaluation of the generated strategies. As shown in the table, we tested multiple stocks, and after 10 iterative rounds of optimization, the system achieved an average return of 25% and a Sharpe ratio of 1.6 across the top 3 strategies per stock. These results validate the effectiveness and robustness of the AlphaTrade framework. Here is our team structure. Chen Zihao serves as the team leader, and all other members have contributed accordingly to their respective responsibilities. Finally, we present the challenges encountered and the lessons learned from this project. Throughout the project, we encountered several challenges. Moving forward, we plan to further improve the system's scalability, stability, and real-time adaptability. At last, our AlphaTrade delivers an adaptive trading framework that leverages multi-agent reinforcement learning to dynamically evolve and refine alpha signals through continuous feedback optimization. Thank you for listening.